In this first mini lecture, I'll give some perspective on how the fundamental principles of chemistry came to be and the history of our understanding of atoms. Most of the content in this lecture will not be tested on, so we cover this material more as a way of introducing the framework for chemistry and to give some perspective on how far we have come over the last few centuries. First, a brief introduction to the symbolic domain of chemistry, so that we can start to understand how to interpret chemical symbols. Each chemical element is represented with an internationally recognized symbol that consists of one or two letters, usually an abbreviation of the name of the element. However, there are some elements whose older Latin names have been replaced by modern-day English names, yet their symbol remains an abbreviation of the older name. These elements are listed in the table on this slide. In my class, I do not expect you to have the names and symbols of the elements memorized, as you will be provided with a periodic table for exams and quizzes that includes the names of all the elements. You can download or print the periodic table handout for this class from the resources page on Scholar. When interpreting chemical symbols, there are a few rules to follow. First, the elemental symbol on its own is used to indicate a single atom of the element, as we see with this first symbol for hydrogen on this slide. If we place a 2 in front of hydrogen's atomic symbol, then this indicates that we are talking about two separate hydrogen atoms that move independently of each other and are not interacting. We will refer to this number on the left side of an atomic symbol as a coefficient. However, if we place a 2 subscript on the right side of the hydrogen's atomic symbol, then this indicates that there are two hydrogen atoms that are bonded together, forming a hydrogen diatomic molecule, where diatomic means there are two atoms per molecule. Finally, if we place a 2 in front or on the left side of a hydrogen molecule, then this indicates that we have two hydrogen molecules for a total of 4 atoms of hydrogen. Note how the coefficient is multiplied by the subscript on the element to determine the total number of atoms that are present. When looking at chemical symbols in molecules, we pay close attention to symbols that have more than one letter and any parentheses that are included in the molecule's notation. CO2 is an easy one. As we can see for CO2, the subscript on the oxygen indicates that there are two oxygen atoms. Since carbon does not have a subscript, there is only one atom of carbon. For PCl3, there is only one atom of phosphorus as there's no subscript, but there are 3 atoms of chlorine indicated by the 3 subscript on the chlorine symbol. Note here that chlorine uses 2 letters, so we want to make sure to interpret this as a capital C and a lowercase l, not an I with the subscript 3. For FeOH3, the OH group is present in the molecule 3 times, which is indicated by the subscript 3. Therefore, there are 3 oxygens and 3 hydrogens present in the molecule. Finally, for the last molecule, note that there are 4 oxygens indicated on the inside of the parentheses, but since there is a subscript of 2 on the outside of the parentheses, this means that there are actually 8 total oxygens in the molecule. Note how we multiply both subscripts to get the total number of oxygens. Note also that there's only 1 chlorine on the inside of the parentheses, so the 2 on in the subscript on the outside of the parentheses indicates that we have 2 chlorines total in the molecule. Chemistry is a fairly modern subject. However, in ancient times, there were many chemical processes that were studied and utilized, but not fully understood. The Greeks would have been able to process natural ore and utilize embalming techniques, but they also thought that there were only 4 elements: earth, air, fire, and water. In medieval times, the study of metals led to several advancements, but alchemists still vainly sought to turn lead into gold, something we now know is near impossible despite our advanced technology in modern times. In the 1600s, Robert Boyle became the first scientist to be thought of as a true chemist, as he was the first to perform truly quantitative experiments with chemical compounds. Boyle's contributions to chemistry include Boyle's law, which we will discuss more at the end of the semester when we introduce the unique behavior of gases, and he also is the first to define an element as something that cannot be broken down into two or more simpler substances, which we often say means it's indivisible. This finally eliminates the Greek philosophy of the four elements of alchemy. 50 to 100 years after Boyle's time, the Frenchman Antoine Lavoisier begins to study the process of combustion and is later dubbed the father of modern chemistry. Lavoisier's law of conservation of mass becomes the first major principle in studying chemistry. The law of conservation of mass states that matter is neither created nor destroyed in a chemical reaction. This means that the total mass of all the reactants should equal the total mass of all the products in a chemical reaction. So, when a reaction takes place in a closed system where matter cannot escape or be introduced, then the mass should not change throughout the course of the reaction. This concept is very important as it allows us to determine the unknown mass of a reactant or product when we know the total mass and the masses of other reactants and products. Some classic everyday examples of this law of conservation of mass can be seen in the production of beer and in your car battery. In both examples, chemical reactions take place within a closed system, and the mass of the system before the reaction takes place is the same as the mass of the system after the reaction takes place. After Lavoisier, another Frenchman by the name of Joseph Proust performs careful weighing measurements during the course of chemical reactions in an effort to study the chemical composition of compounds. Proust's experiments lead to the law of definite proportions, also known as the law of constant composition, which states that a given compound always contains exactly the same proportion of elements by mass. In the following samples of isooctane, which each have a different total mass, we see that the ratio of the mass of carbon to the mass of hydrogen always comes out to 5.33 grams of carbon for every 1 gram of hydrogen. This shows that the composition of a compound is an intensive property. It does not depend on the amount of the compound that is present, but rather is a constant ratio no matter how much of the compound you have. To clarify this a bit more, note that water, which is a compound containing hydrogen and oxygen atoms that are bound together, will have a constant ratio of about 8 grams of oxygen for every 1 gram of hydrogen. So, if a sample of water contains 100 grams of oxygen, then there would be 12.5 grams of hydrogen. However, if we were to study a mixture of hydrogen and oxygen molecules that are not bound together, then this mass ratio between the elements would be variable and would not maintain a fixed ratio. It is due to the nature of the bonds between the atoms in a compound that the composition of the mass of the compound stays fixed. John Dalton comes along towards the end of the 18th century, and he not only contributes yet another fundamental principle regarding compounds, called the law of multiple proportions, but he also combines together all of the other laws up to that point into a comprehensive theory to explain atoms and chemical compounds called Dalton's atomic theory. Dalton is actually credited with dubbing the term atom, which he takes from a Greek word which means indivisible. Dalton's law of multiple proportions extends the law of definite proportions, stating that not only do chemical compounds have a constant composition, but that different chemical compounds that contain the same combination of elements will have mass ratios that are simple whole number multiples of each other. But what does this mean exactly? Let's imagine an experiment where exactly 1 gram of carbon is combusted in the presence of lots of oxygen, and the amount of oxygen that reacts with the 1 gram of carbon is measured. In the first run of the experiment, 1.33 grams of oxygen reacts with the 1 gram of carbon, but in a second run of the experiment, 2.66 grams of oxygen reacts with 1 gram of the carbon. That's exactly twice as much oxygen per carbon as in the first run. So, Dalton rationalizes that this can only be explained by the formation of 2 different compounds that both contain carbon and oxygen. In the first run of the experiment, all of the oxygen combined with the carbon to yield carbon monoxide. But in the second run of the experiment, all of the oxygen combined with the carbon to yield carbon dioxide. The amount of oxygen in the carbon dioxide is exactly twice as much per carbon as in the carbon monoxide. Here's another example. This time, 1 gram of carbon is combusted in the presence of lots of chlorine. In the first run of the experiment, 2.95 grams of chlorine reacts with the 1 gram of carbon. In the second run, 11.8 grams of chlorine reacts, which is 4 times as much as the first run. And in the third run of the experiment, 5.90 grams of chlorine reacts, which is twice as much as the first run. So, Dalton proposes that the 3 compounds that are formed will have varying amounts of chlorine based on the whole number ratios we see between the number of grams, with the second run representing a compound with 4 times as much chlorine per carbon as the first run, and the third run representing a compound with just twice as much chlorine per carbon as the first run. However, note that Dalton is unable to confirm the atomic breakdown of these compounds, as the same results would be expected for this second proposed set of compounds on this slide, as these would have the same relative ratio of chlorine when comparing each compound to the other compounds in the list. Dalton puts all of the previous laws together to form a theory for atoms with 4 major postulates. The first is that the definition of the building blocks of matter, the atom, which is the smallest unit of an element that can participate in chemical change, and that it is not divisible. The second is that atoms of a given element are identical and have a mass specific to that element, implying that atoms of different elements will have fundamental differences in their chemical properties. The third is that the chemical combination of elements to make different chemical compounds occurs when atoms bond together in small whole number ratios. And the fourth is that chemical reactions involve atomic reorganization, but the atoms themselves are not created or destroyed. Finally, at the turn of the century, there is the discovery of the electron, which starts to give a more complete picture of the atom. J.J. Thomson is credited with discovering electrons with his cathode ray experiment, where particles are generated due to an electric field that flow through an evacuated tube, phosphorescing as they interact with the film coating on the inside of the tube. And the positive end of the magnet that is exposed to this beam is able to bend the path of the particles, attracting them. And that the negative end of a magnet is actually able to repel the particles. So Thomson concludes that these particles must have a negative charge, and they are dubbed electrons. You can watch a video with further explanation of this experiment by clicking this link. From the discovery of electrons comes the first model for the atom, called the plum pudding model, as it visualizes an atom as a sphere of uniform positive charge, which is diffuse, and that balances the negatively charged particles or electrons that are dispersed throughout this uniform positive charge. Robert Millikan goes on to use an oil drop experiment to determine the magnitude of the charge of an electron as well as the mass of the electron. And you can watch another video with further explanation of this experiment by clicking this link up top here. Finally, Ernest Rutherford, a former student of J.J. Thomson, conducts his gold foil experiment, which solidifies the modern picture of the atom. In this experiment, positively charged alpha particles are fired at a thin piece of gold foil. Most of these incredibly small particles pass through the foil unhindered, but a few are scattered at random angles, and some are even deflected directly back at the source of the beam of alpha particles. This implies that a dense positive particle must be present in the gold foil, which would be able to repel the positively charged alpha particle. This shocked Rutherford, and he likened this to firing a heavy artillery shell at a piece of tissue paper and having it bounce back and hit you. He explained this by theorizing that the atoms in the gold foil must be made of mostly empty space, but contain a small and dense positively charged nucleus that would be able to deflect the positively charged alpha particles, rendering the plum pudding model of a diffuse positive charge obsolete, as it would not explain his results since the alpha particles should have been able to easily pass through. And so we arrive at the modern view of the atom, which will be the focus of the next mini-lecture. This concludes the first mini-lecture for Chapter 2. Please note any questions you may have about this material and post them to PI.